Alright folks, so in this video what we will do is we will go through the GRPO in detail. Not only we will go through the theory, but we will also do a hands-on code implementation where we will turn a normal LLM to a reasoning model, right? So we'll start with a basic refresher of RL. Then we talk about what are the value functions, what are policy optimization functions. Then we will slowly move into what is PPO and how PPO utilizes both the value function and the policy neural network. And then we slowly go into the topic of GRPO, and we discuss how GRPO kind of moves the value function and how it optimizes the process of training the policy without a value function, right? And in the end we will talk about the code implementation, right? So let's get started. So at first what we will do is we will start with RL refresher. So in case of RL, typically what we have is we kind of take this example where we have a grid world. So this is nothing but a grid world where we have kind of deployed agent. So this is nothing but our agent, and the agent job is to win this game. Now how the agent can win this game is win this game by getting the maximum reward and reaching this position, right? So the agent can take certain steps in the environment, and then the agent can reach a position where the agent will get a reward of +5, and that time the game will end, right? So in between the agent cannot move into a position where the agent will get a reward of -1 and the game will end, right? And also there are certain places where the agent cannot move. So being in a state like here or here, the agent cannot go upwards or sideways to go to this regions of this grid world, right? So with this, let's get started with few of the terminologies of RL. First one is the environment. So the environment is where the agent works upon or where the agent is deployed, right? So in this case, our this grid world is the environment where the agent is deployed, right? So then we have the concept of states. So all these boxes which you see in your screen, like this one, so all these boxes are nothing but states. So you can treat it as like we have some x and y coordinates. So each of these boxes will have their individual and x and y coordinate, which will denote how the state represents in this whole environment, right? So then we have the concept of actions. So actions are what are the possible actions agent can take being in a particular state, right? So if agent lies here, then that time the agent can take any actions going right, going left, going down, and going up, right? So the four possible actions agent can take for being in a particular state. But as I was mentioning, if the agent was present here, then the agent cannot go and take a upward position, and the upward action will not happen in this position, right? The rest of the three actions like going left, right, and down is possible, right? So that is the concept of action. What are the possible actions agent can take being in a particular state, right? So then there is a concept of rewards. So this agent kind of interacts with the environment, and by taking certain actions agent can move from one state to state, different state, right? So if I talk about this one, right? So here the agent was at first was placed here, which is like S1. Then the agent can take action like going upward, and then the agent can reach a state which is nothing but state 2, and the agent will get a reward for this taking this action being in the state 1, right? So that is what the reward is for this action. The reward was like +5. But if the agent was present here and the agent decides to go right, then the agent will get a negative reward and the game will also end, right? So just to make it a bit more interesting, so what we can do is whenever the agent is kind of taking a step in this environment, we will give a reward of -1, right? So the agent can take any path to kind of reach the final state, right? So we don't want the agent to go in an iterative loop where the agent will take a lot of time to reach the final step, right? So what we can do is we can introduce a -1 reward for every step the agent can take, and based on that the agent will decide what is the best possible way I can reach to the final goal, right? So that's the concept of reward. So with this concept, let's go into a concept which is nothing but a value function, right? So as we were seeing in the grid world that we have a lot of states, right? So this individual boxes are nothing but states. You can denote it with certain coordinates, or you can also give it certain name, but this state does not tell you how good is this state if the agent wants to be in that particular state, right? So is it that the state one is better if you compare with other states, and if you have a state which is like S50, if I denote it like S50, is the if the state 50 is better than state 1 or not, right? So if you want to compare different states, so there is no such way where we have defined if any state is better than another state, right? For the agent to be in that state, right? So what we can do is now we can bring in a concept of value function. So using this value function, we will tell, or the agent will get to know whether this being in a particular state is fruitful or not, right? So as we have introduced a -1 for every step the agent can take, so we with that concept we can get the value function for each of these states, right? So the surrounding states which are associated with 5, they will have a value function of 4. Now the surrounding states which are associated with 4, they will get a value of 3. So all these states will have a value of 3, and then we will have the corresponding state values, right? So which we are calling as value function. So that is kind of an indication how a particular state is if we want to compare with any other states from the agent perspective, right? So in that way we can populate all these values and we can get the value function for each of these individual states, right? So I hope you got a concept of how the value function works and what is the need of this value function, right? So it's kind of a future reward which the agent can get for being in a particular state, right? So this value function is what we have done is so far we calculated it manually, but imagine that we have a huge state that is present in the environment. So it's not possible to go through each of those states and manually populate those each of the values of this each of the states that we have in the environment. So what we can do is we can take the help of a neural network, what we call as value neural network. So that value neural network will take the coordinates of a particular state, and given that state as an input, it can give you the value, right? So you can see that we will get the x and y coordinate as input to this value function or this value neural network, and then it will give an output of this value, right? So now the question is how you will train this, right? So what we can do is we can take the help of neural network. So we can initialize this values with some random values which you can see here. Then we will also have the actual values, which is kind of a baseline value of these individual states. Now by comparing these two values, we can calculate a mean squared error between each of this state, and that will kind of indication of how this network will work. So we can take this as like a prediction y hat, and this is like actual y, and then we can do mean squared error calculations, and then we can take an average of it to get the loss for this value neural network, right? So this using this loss function we can train the parameters of this neural network, and we can get a deep neural network which will kind of help us to get the corresponding value function for each of these individual states, right? So slowly by doing a lot of iterations we can do the individual updates of these states, and then we can get a good estimate of what should be the actual value or the closer to actual value for each of these individual states, right? Now let's talk about another concept which is nothing but policy. So if you have this grid world, and this grid world can be solved with by taking different paths, right? So one of the path can be like agent decides to take this path and the agent can reach the final destination, right? Then we can have another agent which will take a different route, and then it will finally reach the final destination, right? Now to compare this two path, how can we decide which is the best path, right? So this policy will tell us which is the best path to reach the final step, right? So this policy is nothing but it is given a state, it will output a probability distribution over a set of actions that you can take in that particular state, right? If we take an example of this particular state, which is S1, where the each of this action is possible, right? So which is nothing but the up, the down, the right, and the left, right? So now the question is, what is the probability associated with this each of this action, right? So is there a function which can help us to decide which is the best optimal action that I can take being in this state, right? So what this policy function will help us to get is that being in a state S1, what is the probability that is associated with the up action. Similarly, we will get the all the individual probabilities for each of these actions, right? Being in a particular state, right? So this for this particular state, maybe it will have the highest value which is associated with up, which is like 0.6, and then we will have the other values, but the sum of this all these probability values should be equals to 1, because this should satisfy the nature of a probability distribution, which is nothing but the sum of the probability should be equals to 1, right? Now the question is, how can we get the associated probabilities for each of this action, right? So for this, if we take the help of previously introduced concept of value function, so looking at the future or the surrounding values, we can decide what should be the my next best step, right? So if I talk about being in this state, right? So if I am on this state, I should not go a direction, I should not take action which will take me the value where the value is 0, right? So I should either take this path or I should take this path, and the down action is also not possible, right? So looking at this surrounding values, we can decide what is the probable action the agent should take being in a particular state. So we can already see that this value function what we have talked about so far, that can help us to decide what would be my policy, right? Or what would be the mapping of the particular actions being in a particular state, right? So using this value function, we will see that we will train some neural network through which we will get a policy distribution for this grid world, right? So as I was mentioning, like if you are in this state, then you can go to this, at first you can go to right, then you can go up, then you can again go right, and then you can again go up, right? So using this path, you can decide this can be a optimal path if you start from here, and then you can reach this final step where you will get a reward of +5 and you will win the game, right? Now let's see how we can train this or we can get the values of this policy, right? So yeah, let's talk about how we can train a neural network to get this policy, right? So we will have a neural network which is nothing but a policy neural network, and then what we can do is we can have two states, like say for an example we have state 1 where the agent is currently standing at, then the agent can take certain action like go to right, and the agent will land up in a state which is nothing but S2, right? So this policy neural network currently it is telling you that the probability that is associated of taking right being in a state is the value is 0.3, right? So which we can see here also, right? So then we can take the help of our value neural network. So that value neural network will tell us that if you move to a state which is state 2, you will get a value of 2, right? We already know that we can have actual value which is associated with this S2. Now we can see that the actual value associated with S2 is 6, right? So after that, what we can do is we can calculate the gain or advantage, which is nothing but this actual minus the value that we got from the value neural network, which is 2. So we will get the advantage as 4. Now using this 4, what we can do is we can update the parameters of our both the network, right? because our value function told us that we will get a value of 2, but the actual was 6. So our value neural network is kind of underestimating the value. So we should also tweak the parameters which are associated with value neural network. And as we are gaining or getting advantage of higher value, then the probability that is associated with this policy neural network, which was zero point 0.3, that we should also need to tweak, right? So what then we will do is, using this gain or advantage, we will update the parameters of our value network, and we will also do the update of our policy neural network, right? So this parameters of the value neural network would be updated, so that the next time the value function will be more closer to the actual, and the probability that is associated with the policy neural network, so that should be also increased to certain values, right? So after doing the weight updates, we can get a value like the probability should be increased to zero point 0.4, and the value after doing the updates has increased to 4, right? So which is kind of better than what we have previously got, right? So this advantage or gain can help us to train both the networks simultaneously, which is nothing but policy neural network and the value neural network. So these two neural network will be trained together. So we will not only use advantage or gain to do the weight updates that are associated with policy neural network. So we will use a concept of surrogate objective function, through which we will do the weight updates which are related to the policy neural network, right? So let's understand how that will actually work, right? So for an example, say that we are doing lot of iterations, like we are playing the game with lot of iterations, and at the iteration 10, probability distribution where the probability of taking right being in a state S1 was 0.3, and the in the next iteration, which is iteration 11th, we get a value of probability which is zero point 0.4 for the same probability, right? Then what we can do is, we can also take the help of value function. So the value function will tell us that the value would be associated with S2 is 2. Then we can take the help of actual value, and then we can calculate the advantage, right, which is nothing but 4. Now to do the weight updates, what we will use is, we will use a surrogate objective function, which is nothing but a ratio of this current iteration probability value divided by the previous iteration probability value, and that we will multiply with the advantage function what we have talked about so far, right? So you can understand that this current iteration value is zero point 0.4, and the previous iteration value was like 0.3. So we will divide 0.4 with 0.3, and then we will multiply with the advantage term, right? So then we will get this loss, which is nothing but 5.33, and using this loss we will do the weight updates which are associated with the policy neural network, and we will hope that the next iteration we will get a higher probability associated with this particular state and action pair, right? So if you take an example of that, instead of previous iteration value of zero point 0.3, we had the previous iteration value of 0.1, right? Now if we use this objective function, we will get a different value. So now we will divide 0.4 with 0.1, and we multiply with the advantage, and we will get a higher value, which is nothing but 16, right? So because the previous value was 0.1, and just to get a higher probability updates, we will have a higher loss, or this value is much more higher, and using this we will do the weight updates in subsequent way, so that the next time the probability would be much closer to the actual probability that is associated, right? So I hope you got an understanding of how the previous iteration value would be used to calculate this objective function, and that we will also use in case of PPO also, right, where we take the previous or the old policy value in consideration, and based on that we will do the newer updates that will happen in the network. Now if you talk about the PPO, which got famous when the ChatGPT used it for the RLHF alignment. So this PPO uses this objective function, which objective function we have almost covered everything. So this is nothing but what we have talked about the previous iteration and current iterations probabilities, and using the previous iteration values we will calculate this ratio, and then we multiply with the advantage function, right? So which we have already talked about. And then what the new concept here is, we will address a cliff function here. So this cliff function will ensure that the whatever the calculations that are happening inside this ratio, that should stay in a range, right? So if this a ratio is either too large or too small, then it should clip in a range so that the value would be lie within this range, right? So this is the middle value, and these are nothing but epsilon what we have decided, 1 minus epsilon and the 1 plus epsilon, right? So this value is 1, and these are the ranges where we will clip these values, right? So all these things what we are doing here is to achieve the stability in the training of this reinforcement learning algorithm, right? So we don't want our newer policy to deviate so largely from the previous policy, and also we don't want our ratio to be greater than or smaller than certain range, right? So that's why we are using these two things, and we are also taking the minimum of these two things to get the final value, right? So this will ensure that the values are within certain range, and we will get a much more numerical stability while training this neural network, right? So in case of PPOY, we call it as proximal policy optimization, because we are kind of maintaining the proximity with the previous policy that we have had in the previous iteration, right? So this using this, the PPO would be trained using this optimization function, and we will achieve the training stability by avoiding too large policy updates. And also we will use a ratio that will indicate the difference between our current and old policy, and the clipping this ratio in a specific range will ensure that we will have numerical stability while training the neural network, right? And all this is to ensure that we do not fall off from the cliff while doing the updates, right? So the aim is to reach at the top of this cliff, but while doing large weight updates, we should not fall off from the cliff, right? So once we fall off from the cliff, then we cannot recover and come to this path. So just to ensure that we do not fall off from the cliff, we have this ratio function and also the cliff function, which will make the policy updates much more stable, right? So now we can finally move into the concept of GRPO, right? So with this lot of groundwork, now we have the base to cover the GRPO. So if we take the comparison between PPO and this GRPO, we can straight away see that this value function or this value model we do not have here, right? So this GRPO kind of eliminates the need of value function, and how it eliminates is that we will slowly talk about in the next few minutes. But if you can understand that in the GRPO, what we are doing is we are getting a question, and based on that question we are generating multiple outputs, right? So these outputs are nothing but group of outputs for this particular question, right? And we also get corresponding rewards associated with these outputs, and based on that we do the calculation of the advantage. So previously, while doing the advantage calculation, we need to get input from the value model, and based on that we will calculate the advantage, and using that advantage we will do the weight updates at the policy model and also at the value model, right? But in case of GRPO, we will not have this value model, so we will calculate the advantage function in a different way, right? So which we will talk about now, right? So this is how the GRPO objective function looks like. So you can already understand few of the things that we have already talked about. So I'm sure this part is now you can understand. So the new thing that you can see in this equation is this DKL, which is nothing but the KL divergence, which will ensure that whenever we are doing the weight updates, it should not move too much away from the actual policy of the base model or the reference model, right? So this is just to avoid the reward hacking that generally happens in case of RLHF, where the model kind of learns to cheat and get higher rewards. So just to avoid that, we can introduce this concept of KL divergence. So there are a lot of videos on the internet, you can go and look through this concept. So I will just tell you that this is just to make sure that we do not to deviate too much from the base policy, right? Let's talk about how this advantage is calculated in case of GRPO, right? And how this advantage calculation looks. So we can have several set of questions which are like Q1 to Qn. Then what we can do is we can sample a question from this set of questions, and based on the particular question, which is nothing but Q1, we will generate different responses or output, right? So we can, for this example, we will have O1 to O4 as an output, and for each of these outputs, we using a rule based reward, we will calculate the reward, which is like R1, R2, R3 and R4. Rule based reward values can be 1.0, which is like for correct and well formatted response. So the R1 and R4 which are associated with O1 and O4 will have higher rewards, and the other two outputs which are like O2 and O3, which are correct but less formal, and also the O3 is incorrect answer, so there we will have lesser rewards compared to the O1 and O4, right? So once we have this rule based rewards, what we can do is we can calculate the mean value of these rewards. So we can calculate also the standard deviation. So we can see that the mean value is 0.725 and also the standard deviation is 0.453, right? So once we got the mean and standard deviation of this reward, so what we can do is we can use this advantage function where for individual rewards we will calculate the advantage, right? So using this formula like reward of an answer minus the average reward in the group and then divided by the standard deviation of that group, we can calculate the individual advantage function, right? So here this is nothing but the group which we are talking about, and this is the group of rewards that we have for this particular group of outputs, right? So now once we have this formula, we can calculate the individual advantages, which are nothing but A1, A2, A3 and A4, and we can see the advantages that are available for each of these outputs, right? So whenever we get a positive advantage, that means the answer is better than the group's average, and whenever we get a negative advantage, that means the answer is worse than group's average, right? So with this, what we are doing here is we are generating a group of outputs, then a group of rewards, and within that group we are calculating the advantages, and looking at the advantages whether they are positive or negative, we can decide which output we should select at the next iteration so that we get a higher reward, right? So in the GRPO, the main aim is to update the policy to favor the responses with the higher advantages, right? So this algorithm will encourage the competition within the group by driving the model to generate better responses without a value neural network, right? So here we can see we do not have a value neural network which was previously help us to calculate the advantage or the gain in case of PPO, right? So we can throw away that very complex looking neural network, and by using this rule based reward and the group of rewards, we can get the individual advantages for within a group, and then we can do the policy updates to get a uh, RL algorithm, which is nothing but GRPO, right? So I hope with this you got a good understanding of how the GRPO works. So as I was mentioning, we have the rule-based rewards. So we can have different rewards. So in the coding example also we will see in detail what are the different rewards, but we can have accuracy reward which will tell if the answer is correct or not. Then we will have a format reward. So using that format reward, we will check if in the answer there is a response or answer tag present or not, and based on that the reward would be generated. And also we will have a concept of language consistency reward, which tells us that if the answer is generated in a single language or not, right? So this was introduced to tackle the issues which are related to DeepSeek R10, where like a lot of languages got mixed in the answer. So just to avoid that, the DeepSeek R1 paper also introduced this concept of language consistency reward, right? So which will avoid the language mixing or incoherent formatting in the output, right? So with this, let's move into the coding part where we will implement a code which will turn your normal LLM to a reasoning LLM. Okay, now let's move into the code implementation. So in this code implementation, what we will do is we will get the Queen 2.5 instruct model. And what we will do is we will turn this Queen 2.5 instruct model to a reasoning model where we will use the GRPO to train in such a way that the answer will include a reasoning part and it should generate more better answer using the reasoning part, right? So this credit of this notebook are lot to go with the Unsloth notebooks that are hosted in their GitHub. So I took the reference of those notebook and I did some modifications to create the same. So at first what we will do is we will do the installations of this Unsloth and VLLM, and also we will leverage the TRL library that is from Hugging Face, right? So at first what we'll do is we will download the model, which is nothing but Queen 2.5 3 billion instruct model, and so that we will download using the Unsloth library. So using this fast language model from pre-trained, we will get this model and get the model and also the corresponding tokenizer for this Queen 2.5 billion model, right? So then what we will do is we will do the fine tuning using a PEFT model. So in that PEFT model, what we will do is we will use a LoRa rank adapter. So using that, we will train the different modules of this Queen 2.53 billion instruct model. So you can see these are the set of modules that we will use to fine tune our model, right? So instead of training everything, we will target few of the modules and that we will train to tune this model to make it a reasoning model. Once this initialization is done and the definition of the target modules are defined, then what we will do is we will create system prompt. So in the system prompt, you can see that we have designed the prompt in such a way that it should have a thing tag and it should also have a answer tag, right? So then we will move into the data preparation step. Data preparation step, we will leverage this GSM 8K data set, and using that data set, at first what we will do is we will look into that data set. So it's nothing but few of the question and answer which are related to math. So you can see the first 5 questions. So at first it will have a question, then it will have an answer, and in the end the actual answer we will have with a few of the hashtags, right? So which is nothing but the 4 hashtags, then the actual answer would be present, right? So the answer will have the reasoning part at first, or the chain of thought prompting, and then it will have the answer, right? So then what we'll do is we will create a function which is extract hash answer, which will look for this 4 hash, and based on that it will extract the exact answer, right? So then we have is we will create a data set where we will leverage this system prompt what we have defined, and based on that we will create the prompt and response pair, right? So using this function we will pass our data set and we will get a final data set which will have this prompt and response pair, where the prompt will have the system prompt which will kind of force the model to think in terms of a reasoning model, right? So then we can see this output. So you can see the question will have this, then the system prompt will be there, like respond in the following format, where the tags will be present, and then the question content will be there, and finally it will also have the corresponding answer, right? So now the data preparation is done. Then what we'll do is we will define our reward functions, right? So as I was mentioning that this DeepSeek R1 uses the concept of rule based reward. So you can define set of rules, and based on that the final reward would be calculated, right? So one of the reward that we can have is the correctness reward function, right? So it will get the question from the prompt and it will also take the completion, and based on the completion it will extract the answer, then it will check if it is equal to the actual answer and not, and based on that it will give certain rewards. So you can see for correct answer it will give a reward of 2.0, and for wrong answer it will give a reward of 0. We will have this int reward function. So it will check if the answer that is generated by the model is integer or digit or not, right? So if it is a digit or integer, then it will give a reward of 0.5, else it will give a reward of 0, right? So then we will check certain format related rules. So at first it will take the completion, and in the completion it will have this pattern check. So that pattern will check if there is a thing tag or an answer tag that is present or not. If those patterns are present, then it will give a reward of 0.5, else it will give a reward of 0, right? So then we will have a count XML reward where it will make sure that we have all the tags present only one, like the opening tag and the closing tag should be present once for both thing tag and answer tag, and based on that a reward would be calculated, right? So then what we will have is we will have a XML reward function which will use this count XML function, and it will calculate the reward, right? So all these reward functions we have defined. Now you can add or delete any of these reward functions, and we will see how to integrate these reward functions in the GRPO side. What we will do is we will leverage this TRL library and we will define the GRPO config, right? So in the config we mentioned that we will use the VLLM, which will help us to do the faster inference and the faster training. Then we will define what would be my learning rate, what would be the optimizer related parameters. Then we have the weight decay parameters and all the parameters that are associated with training the GRPO, right? So you can see we will train this model in the Google Colab free tier. So we will train it for a maximum length of or a maximum step of 250, and we will log the reward values and the output from the model for every one iteration, right? So you can see the logging steps is equals to 1, right? And based on that what we will do is we will now create a trainer. So that is nothing but the GRPO trainer, which will take the model as one of the parameter, then the tokenizer, then we will give the reward functions, right? So all the reward functions that we have created previously, the XML count reward, the soft format reward, the strict format reward, the int reward, and the correctness reward, right? So all we will club and we will pass it as a parameter to this reward function, right? And we will mention what are the training arguments and also the data set that we have prepared, right? And after that we will start training the model, right? So once we start training the model, so it will give you an output where it will tell you the number of steps, then the training loss, then the reward, then the standard deviation of the reward, and also the completion length, right? So the higher the completion length, so the better the model will think. So the model will think more if the completion length is higher, right? And also we have the corresponding KL divergence loss also, which we can track, right? So you can see that it starts with very negative reward like 0.20. So once we reach a step where we have done at least 100 iterations, then we can see that the third column, which is nothing but the reward column, there we start getting a positive reward of like 3.5 or 2 point something. So in that way the model is kind of learning and it's generating the output which is ensuring that the model is getting higher rewards, right? So it's moving into that trajectory where it's getting into the higher region of rewards, right? So once that is done, then what we can do is we can start making inferences, right? So we have sent a question, and that question is like how many R's are there in strawberry. So it's asking the model to calculate the number of occurrences of R in the word called strawberry, right? So at first what we'll do is we will use the base model. So we will not use the LoRa adapter that we have trained for the reasoning part. So you can see the LoRa request is equals to none. So that means we will not use the GRPO related LoRa adapter, and based on that we will make inferences, right? So you can see it tells you like there are no letter R in the word strawberry, right? So this is using the base model. The model output is not correct. So the answer should be 3, but it tells you that there is no R that is present in the word strawberry, right? And you can also see there is no thing tag, there is no answer tag. So it's a simple instruct model output that we have got so far, right? Now, as the model was trained with GRPO using the load adapter, we can save that model and then we can make inferences using this model. We can see in the LoRa request, we have mentioned that model.load LoRa, and we mentioned the name that we have saved in the previous step, right? And then we can start making inferences using this model. And we can see we are getting this thing tag where it's going through a thinking process. Like in the word strawberry, there is only one instance of the letter R, and it appears in the middle of the word, right? So you can see that it's doing some sort of reasoning. It's not totally correct, but it started doing the thinking after 250 iteration. So this model typically gets trained for a lot of epochs and a lot of iterations. So we have only trained for 250 max steps, and based on that, it started generating the thinking process and then the answer also, right? So we can see that the think tag and the answer tag is present, and it done better than the previously discussed model, that is the base model which we have started with, right? So with this you can train any model, and you can train any base instruct model to a reasoning model with the steps that is covered in this video, right? This is all I wanted to discuss in this video. Like, we started with the definition of how the basic RL works, then how the PPO works with the help of value function and the policy neural network function. Then we talked about GRPO, how the how GRPO kind of eliminates the need of a value function. Then we move into the coding part, where we took a Quinn 2.5 instruct model and that we turned into a reasoning model where it started doing the reasoning, and based on that the better answer was generated compared to the base instruct model, right? So with this I will end this video. If you have any questions, comments or doubts, let me know in the comment. So I will try to answer that. Thank you. See you in the next video.